Hi, so in this presentation we will discuss about iron oxide, their nanoparticles, and the effect of size and surface properties on magnetic uh, behavior of these nanoparticles. And then we will discuss about alignment and self-assembly and their application in biomedical field. So there are 16 phases of iron oxide, but there are only 4 that are crystalline in nature, that are meghemite, magnetite, and then geotite. So these 4 are crystalline in nature. You will learn this during your XRD studies. How do we make them is basically through redox reaction. That is, you use single or double precursors, and then you react it with any base, strong base, and then you will get these nanoparticles. Today we will just discuss about their magnetic properties and how they influence in different reactions. So these magnetic properties are due to the presence of 2 or 4 or 3 single electrons in the D shell, and when they rotate in the D shell they produce magnetic effect. And how can we use these surface properties is that we can charge, like there is a charge on the surface of these nanoparticles, and then we can have interaction with ligands like oleic acid, which will have a hydrophobic tail. This helps these solutions to make a stable solution, stable colloidal solution. And then we can also use 2 other techniques, that is heating and decomposing these nanoparticles with ligands, so that you can change the functional groups. And you can also use solvents, but then you have to use centrifuge so that they can also make stable colloidal solutions. How the size affect the properties of magnetic behavior of these nanoparticles. So basically there are 3 types of magnets: ferromagnet, antiferromagnet, and ferrimagnetization. So it all depends on if the electrons are moving in same direction or in different direction, and how they behave when they are in the electrical field. So magnetite is the most magnetic in nature, and you have his formula here. It have both iron particles like Fe2 and Fe3. And now we have to calculate how much magnetic property does a nanoparticle have. We calculate it using this formula, which tells us the magnetic dipole moment per unit volume. And then it always depends on how these nanoparticles behave in external magnetic fields. So we can see this here, that if a particle is of a larger size, it will have different lattice and electrons will be moving in different directions. And when you provide an external magnetic field, they can have different directions of motion. However, when you reduce the size, you see that the size of area in the hysteresis loop is reduced, and this is the superparamagnetic behavior, which is more visible at nanoparticle size. How do this effect is when you change the magnetic field, external magnetic field, so these nanoparticles behave in a very specific way, and this dictates the time of a complete magnetic spin. So if there's a less time, then less energy is released during the process, and then it have more efficiency. Now thermal energy for switching these magnetic properties are also important. So we calculate it using the transition probability between 2 directions, and then the time it takes to spin from north to south pole and then again to north pole. So we create a balance between kV and kT, so that the average time of magnetization is reduced. So what we do is then we calculate the K magnetization, which is almost like 1.8 10 raised to power 4 for magnetite. Then we can calculate the average time it takes to rotate between north and south and again to north pole. Its application in biomedical field is not like in a naked form. So what we do is we put them into a plastic matrix to make beards, which have a lot of nanoparticles of small size, and then we use them and it have a better control. So the definitions for paramagnetization is that these nanoparticles will exhibit a higher magnetic behavior, but it can have a bigger volume under it. However, superparamagnetic is those nanoparticles which not only exhibit high magnetic properties but also very small hysteresis loop. So then there is another effect which is related to the formation of the shapes of these nanoparticles, that is Kirkendall effect. How it affects is that when you have combination of nanoparticles, you dope it with oxygen atoms, and then because of the surface charge properties, a void is created, and when the time is collapsed, like when you let it have more time, then there's a void created in between these combination of nanoparticles, and that have a very special effect in medicine. Another interesting property of nanoparticles is the self-alignment. Now you have nanoparticles, and these nanoparticles are coated with ligands. Now when you start to evaporate it with liquid, the nanoparticles start to align themselves in such a way that they have very nice geometry, and these nanoparticles are separated from each other, and it have very high surface area and is used a lot for catalytic reactions and in medical field. So how do we use these kind of nanoparticles is that we make a magnetic bullet by encapsulating these nanoparticles in some kind of medical materials, and then we add it into, like we dose it to the patient, and then what happens is when the coating is dissolved, these nanoparticles become active, and then we apply external magnetic field to manipulate the motion and properties of these nanoparticles, and it always depends on the motion of north to south and again to north pole to kill tumor, and it's very successfully applied in medical field. Another aspect is the rotation of these nanoparticles when magnetic properties are like external magnetic field are applied in different directions, as you can see from first picture. So application of this kind of properties of nanoparticles is used to produce the magnetic resonance imagings, MRIs, which are very famous in medicine. So here you can detect the tumor in brain. What we have learned today is iron oxide nanoparticles are easy to synthesize. Then you can manipulate the surface properties